Hello and welcome to Stanford Scholars Talk on Zooids, Building Blocks for Swarm User Interfaces. This paper considers the design and potential of tabletop swarm user interfaces through an open-source, open hardware platform called Zooids. Currently, there are several related but limited areas of research in terms of human-computer interfaces that deal with physical display and interaction. Before we dive in, let's explore existing user interfaces. The first is tabletop tangible user interfaces, where tangible objects on a flat display act as controllers to reflect a graphical display. Users can move these tangibles across the grid and see their position reflected on the screen. The second example, shape displays, use larger physical surfaces to reflect user input via their changing geometries. Let me try to help you imagine that. I hope that helped. Finally, swarm robotics is a new approach to the coordination of multi-robot systems consisting of large numbers of simple physical robots. Generally, mini robots and swarm UIs can be used to achieve bigger goals by moving in groups or specific formations. This tactic achieves an age-old vision for robots to collectively display an output, and therefore act as physical matter. There's already extensive research into different types of related human-computer interfaces. So why are Zooids different? They introduce a concept called swarm user interfaces, which is defined as a collection of human-computer interfaces made of independent self-propelled elements that move collectively and react to user input. This picture shows how Zooids can form a swarm user interface and be used to move small objects, such as mobile phones, from one place to another. Sounds cool, right? Let's have a look at hardware design. Zooids are 26 millimeters in diameter, 21 millimeters in height, and weigh about 12 grams along with their small battery. It uses motor-driven wheels and contains a flexible electrode for capacitive touch sensing. A networking chip is used to communicate along with a main computer. Here's the overview of Zooids' software architecture, which has 4 main layers and communication structure. So how do they communicate? At the application level, the desired positions of the robots are computed. These desired positions are transmitted to the simulation layer through a network socket. Based on the chosen control strategy, the simulation layer computes the goal positions of the robots, either final positions for PID or intermediate points for HRVO, and sends them to the server. Finally, the server layer dispatches commands to the individual Zooids while at the same time monitoring their status and position. This figure gives an overview of the design space of swarm interfaces. They can be organized into interaction, display, and environment aspects. Inspired from vector graphics tools, the authors have implemented a swarm version of a freehand drawing tool to simulate the swarm user interface created. Initially, the freehand drawing Zooid stands in the center of the working surface, while unassigned Zooids wait at the top in an idle state. The user then drags the freehand drawing Zooid, and the previously idle Zooids move to the path of the drawing Zooid to form a physical trail. When the system runs out of idle Zooids, the trail follows the freehand drawing tool like a snake. The curve can also be deformed by dragging its constituent Zooids individually or by moving many of them simultaneously. This slide shows the example of a circle tool, where 2 control points are used to define the circle's diameter, and idle Zooids are automatically positioned to complete the circular shape. Zooids are automatically added or removed, depending on how many of them are necessary to construct the shape. Quite smart, right? But they have many limitations as well. Zooids' first limitation is that they have an external projector for tracking, adding cost and additional hardware that impedes their scalability. Additionally, sensing of input is limited to capacitive touch, so only sensors touching a user's hand will be activated. As size decreases, the power supply decreases and becomes problematic. Zooids have a non-holonomic drive, meaning that they cannot move freely in 2-dimensional space, and instead must turn to a specific heading, like a car. Finally, the interaction area is limited to flat surfaces with a minimal amount of traction. That's about all for limitation, but now we'll move on to future work with Zooids. In the future, the researchers will pull inspiration from ants to simulate their behavior in Zooids. Moving forward, sensor function will aim to allow for richer interaction techniques, leveraging the direct manipulation of many robots at once. The current system relies on individual chargers, so researchers aim to integrate wireless charging coils so robots can charge autonomously. In order to achieve smaller size, researchers will need to move away from geared DC motors with wheels for locomotion to other actuations such as piezo actuators. This marks the end of our talk. To view more of such talks, please visit scholar.stanford.edu. Thank you for watching.